Pleasure to be here with you on this 40th anniversary. I've been looking forward to it for a few years, realizing, gee, it's been 40 years. In fact, I've heard people say that the eruption of Mount St. Helens is now over the hill since it's had its 40th birthday. And I'm thinking, yes, maybe in a human time frame, 40 years is over the hill, but in a volcanic time frame, it's nothing. So if you, those of us who were around to witness this, we really witnessed something special. It may happen once in a lifetime. It may not even happen within your lifetime. So it's really remarkable that we got a chance, to see this. So I'll start out there with that. And this presentation is entitled Mount St. Helens Then and Now. So we'll, and here's my contact information. And okay, I'll get started. Mount St. Helens was the most destructive volcanic disaster in recorded US history. And that means, ever since we've been the United States, this was the biggest eruption that we had in the lower 48. Okay, so what we're going to do in this presentation is learn about stratocone or composite cone volcanoes, the type of volcano that Mount St. Helens is. We're going to examine the events leading up to the 1980 eruption. We'll see this big one and its effects on the landscape. And then we'll look at activity since 1980, and we can even speculate a little bit about the future. Okay, so before 1980, Mount St. Helens was called the Mount Fujiyama of the US because it had the perfect stratocone shape. It had just perfect cone shape here that you can see. And that told geologists studying it that it was a young volcano. And in fact, it was predicted that it would erupt in the late 70s. People working on it predicted that it would be the next one to erupt, but they didn't have to wait very long. Okay, the mountain sported the shape and the perfect symmetry of a stratocone volcano. So you can see Mount St. Helens here, what it looked like in the foreground, and in the background you can see Mount Rainier, which is much more rumply looking because Mount St. Helens has that young shape, that perfect symmetrical shape. Told us that it was a young volcano and therefore probably the next one most likely to erupt. So before the eruption, Spirit Lake was America's playground. There were all kinds of Boy Scout camps around there, cabins, and it was really a happening place in the summer. So what we're going to do with this program and this lecture is we're going to recount the events that took place to change something like this into this in a matter of minutes. Okay, so first a little bit of geology background here. Composite cones, the type of volcano that Mount St. Helens is, also known as a stratocone, are made of layers of volcanic material. So stuff erupts from the volcano, and if it gets ejected into the air, we call it tephra. And then lava comes over, and kind of glues it all together. So I like to think of it as Rice Krispies, a pile of Rice Krispies, so assuming that cone shape, and then lava coming over it and kind of gluing it all together. Think of it as Rice Krispies and Karo syrup, and then hardening. And this happens over and over to build the cone. So I want to show you an animation that I have here of how these things build up over time. And it takes many, many eruptions to build up a layered stratocone volcano. Okay, so what you can see then, why they call it stratocone, because we've got different layers of different material. And this is what they do. They build themselves up And then eventually they have a catastrophic eruption. And we'll talk more about that later. Now, where does this material come from? And where are we getting this molten magma? We call it magma when it's under the ground, and we call it lava when it comes to the surface. But where is this stuff coming from? It's coming from chambers down below the volcano. And in the Pacific Northwest, this is coming from I'll talk more about that in a minute, but you can see the process here is called subduction. So when we have two tectonic plates coming close together, and one of them is more dense than the other one, the denser oceanic plate dives under the continental plate, and that creates some melting. Now, it doesn't melt all the rock there, but it's bringing down water with it, and it's causing melting, partial melting to happen. Now, magma, because molten rock is less dense than solid rock, it makes its way to the surface and it collects in magma chambers underneath the volcano. If and when it ever breaks to the surface, then you have an eruption. So it has to find a way to get up there and break the surface, as it often does. So in the Pacific Northwest, the magma chambers that are feeding Mount St. Helens are from the tectonic plate that's off our coast called the Juan de Fuca plate, and it is diving under us, which we are on the North American plate. And that is creating the whole chain that we know as the Cascades. Okay, so we can see that Mount St. Helens up here, but we've got a whole chain starting from British Columbia and going all the way down into Northern California. Now, the older Cascade Range, the Cascade Range itself has been around for a long time. It started, and we've got in Oregon, we've got remnants of the Western Cascades, started 40 million years ago. But the peaks that we know of as the Cascades are considered the high Cascades, and they're younger. And what they're doing is they're building up upon layers of older volcanoes. So we've been having a volcanic range for 40 million years, and individual peaks have come and gone over that period of time. So Mount St. Helens is considered to be a pretty young cone, being 40,000 years old when it started building it up. And you can see here that it's built on layers of volcanic material from those older volcanoes. And this, I've got a picture here that I took with Mount St. Helens would be over here on the right. And so this is the adjacent bluff that's facing the north side of Mount St. Helens. And you can see the layering in here. Okay, so the blast of 1980 stripped away a part of this hillside, and you can see the layering. Okay, so during the last 4,000 years, we've got records of all these volcanoes and how often that they've erupted. And you can see, Mount Hood, for example, erupted about 2,000 years ago, and then within the last 200 years. But it's really easy to see which one is the most active one. Okay, so by far, Mount St. Helens has had the most eruptions in the last 4,000 years. Okay, so we're going to talk a little bit about predicting volcanic eruptions and how do we predict them. This becomes when a volcano starts acting up, this becomes the most important question, is when is it going to erupt? And so we look for things. We start noticing bulges on the flanks of the volcano. So we notice ground deformation, places of swelling, and so forth. There's a dramatically increased heat flow around the volcano. So as that magma moves up into the cone itself, or it starts moving up, it increases the heat around there. There's also changes in local gravity because gravity isn't, magma is lighter than dense rock. And there's gas and steam eruptions. So you can smell it, sulfur dioxide, carbon dioxide, and water vapor. So it lets off eruptions as well. But seismic activity has proved to be the most efficient way of predicting volcanoes, and that would be earthquakes. So there'll be multiple small earthquakes before the eruption. And then once it gets to the point of harmonic tremor, or what is called long period seismicity, then we know it's getting close. In 1989, so 9 years after the eruption, Mount Redoubt in Alaska was the first one to be accurately predicted by using this long period seismicity. So when magma is moving up into the edifice, into the volcano, it gives off sort of a humming vibration. So this can be noticed in the seismic record. Normally the seismic record has you know, going up and down with the shaking and then tapering off. But the harmonic tremor kind of lasts for a while. It has the initial jolt, and then it takes a long time for it to slow down. And when they start seeing these in the geologic record, then they know that the eruption is close. And in 1980, it was I don't know actually the background on the seismicity of this, but by 1989, folks from the USGS were working on this long period seismicity. And a geologist down at Menlo Park, Bernard Shuey, I'm not sure how to pronounce his last name, but he predicted this. He started seeing the readings from the seismic signals from Mount Redoubt up in Alaska, and he was certain that this meant that an eruption was very close. He was so certain, his colleagues finally cajoled him into calling up there. They said, well, if you're so concerned about it, why don't you call up there? So he made a telephone call up to the AVO, the Alaskan Volcanic Observatory, and the person that answered the phone said, I can't talk right now, the volcano's erupting. So by that, he would, you know, this is the best predictor. When we know a volcano is going to erupt, there's a lot of nervousness and wondering, but you can't pin it down exactly. This method, now it doesn't always work on every volcano, but it's one of the best indicators we have that the eruption is getting very close. Okay, so what we want to do then is look at the big blast, and that caused several volcanic disasters. So I'm going to examine the events leading up to the eruption, and then we'll talk about some of those volcanic hazards. In March of 1980, they started earthquakes started increasing, and so that we knew that magma was on the move. So by early May, a body of magma had lodged in the volcano here, and it's going to find the weakest route. It's cracking rocks. That's what causes earthquakes. It's cracking the rock as it's moving upward, and so it finds the weakest spot. And in this case, it happened to bulge out towards the north. And so we started seeing this bulge. You can see here where the top of the crater kind of sunk down, but the north slope of it started bulging out. And you can see, and we could track it here and watch it. So now what happens is if you make a bulge here and you make the volcano more steep than it can hold, it has a certain angle of repose that the material is stable at. And if you oversteepen it, you make it unstable. Okay, so what happened early on the morning of May 18th, was they had a larger than usual earthquake. They'd been having earthquakes all along, but now you've got this really over-steepened bulge, and they had a larger earthquake, and that was just enough to start the landslide. So this whole bulge area started moving downhill in the largest landslide that we were able to witness in recorded history. Not the largest one that's ever happened, but the largest one that we were able to view. And so after this bulge came off, after the whole north slope of the mountain failed, then that initiated the eruption. So the magma's under there building pressure and building up gas, and then having the landslide happen is like taking the cork off the bottle after you're shaking it up. And so that initiated a vertical eruption later, but initially a lateral blast, meaning that it shot straight out the side. Okay, so let's just talk for a little bit about that lateral blast. And a smaller one had occurred earlier in the volcano's history, but in 1980, it was basically unheard of. I think there had been one up in Russia that had done that. There was some stuff in the literature about it, but basically they weren't thinking of it and weren't really considering it. So the extent of the area that was affected by the initial eruption was unexpected. They certainly would not have put Coldwater Tower 2 there, you know, in harm's way had they known that it was going to shoot straight out the side. They placed the tower there so they could get a good look at the bulge that was facing toward them, but you know, they didn't expect it to shoot straight out like that. So after about an hour, enough of the volcano had gone away to where the eruption could become a full vertical eruption, as most people, that's what they expect when they see, you know, they expect an eruption to go up, but didn't always. Okay, this was taken, there's a view of the mountain just right before it erupted, and this was where they placed the observation tower. Today we call it Johnston Ridge in honor of David Johnston, who lost his life. Okay, so what we're going to do here is we're going to examine the sequence of events and photographs here. So I'm going to show you the bulge developing, and then I'm going to show you the landslide that gets set in motion by the earthquake. We'll look at the vertical eruption and the lateral blast initiated. And then we'll see that the lateral blast is moving faster than the landslide, and so it overtakes the landslide. And then we'll see it completely overtake the landslide. So all of these are the famous pictures from Gary Rosenquist. And this is what it was right before the eruption. Now you can see that the top of the mountain has kind of sunken down, and you can see the bulge here on the north slope. And then all it took was an extra big earthquake to be what set off the landslide. So the landslide, the whole north slope of the mountain begins to fail. And for people observing it, it looked like it was just rippling. And you can see, we see the remains of it now in the Toutle River. It filled up the Toutle River to about 150 feet higher than it used to be with all this material. Okay, the vertical blast, and a second later, this is what it looks like. The vertical blast and the lateral blast is initiated. And so we can see the landslide here, but then we can see the lateral blast starting to come out and a little bit of a vertical blast too, but within seconds later, that lateral blast is moving faster than the landslide and it completely overtakes it. So this is, you know, this is a big thing. This is a dramatic looking volcanic eruption. Let me show you after about an hour or so, I'm not sure on the time frame, but fairly quickly after that, enough of the volcano was gone that then it actually went up in the air as a vertical eruption, reaches more than 12 miles up into the atmosphere. Okay, so all in all, in the 1980 eruption caused the mountain to lose almost 1,200 feet, you know, 401 meters, almost 1,200 feet from its summit. So the original summit of the volcano was here, and now we've got a little bit of a ring, and then we've got a big crater in here. Okay, I got this picture. I've been giving this lecture for a long time, and I had somebody contribute this. So this was a man named Charles Hall who went to view the volcano. He knew that it was going to erupt, and he took his young son, and they happened to be on the south slope of the volcano. So all the action is happening away from him, taking place, and so he was perfectly safe and was able to shoot this picture, which is just amazing. And he gave it to me to share. Just impressive. His son, I think, was about 12 years old at the time, and became a geologist after looking at this. This was just, you know, just you know, and he was in a safe place here. You can see that the south slope of the volcano was virtually untouched, where the north slope is what suffered all the devastation. So if you were impressed with the size of that, and I hope you were impressed with the size of that, let's look at how it really shakes out compared to other eruptions. So we have, here's the eruption that you just viewed. And this is in terms of, well, this isn't done with the BEI. I'll explain that later. But this is just kind of a visual image to show the different sizes of volcanoes. In 1991, Mount Pinatubo in the Philippines let out a blast that was, you know, quite a bit bigger than the eruption that you just witnessed. Mount Tambora in Indonesia, the year 1815 was called the year without a summer. It put so much material into the air that it cooled the planet for a whole year. And starvation was the result of it, just incredible. And then if we want to take it even farther and talk about supervolcanoes, this is what Yellowstone's last eruption would have looked like in comparison. So as tremendous as this was, it was really small, fairly small in the grand scheme of things. But for us, it was very big. Let's look at measuring the eruption and the volcanic explosivity index, which is a way of measuring how big the eruption is, a way of quantifying it. It's very similar to the Richter scale for earthquakes in the sense that it's a logarithmic scale. It measures two different things. It measures the amount of volcanic material that's ejected, and it measures the height, how high it goes, so the height of the eruption column. And with those two factors involved, we can come up with a number for it. And it is a logarithmic in scale, meaning that a 2 is 10 times bigger than a 1, and a 3 is 100 times bigger, and a 4 is 1,000 times bigger, and so forth. So we're going to compare eruptions. Most of the volcanic eruptions that we see in Hawaii are a VEI of 1. Mont Pelée on the island of Martinique, 1902 was a VEI of 4. Mount St. Helens, the 1980 eruption was a VEI of 5. Mount Vesuvius, that buried Pompeii, 6. Krakatoa, 6. Now we're getting pretty big. And Tambora, the one that I said caused a year without a summer, a VEI of 7. And Toba, also in the Philippines, last eruption was a long time ago, but on a huge scale. So as tremendous as this was, it was, and then Yellowstone would be on that scale. It was really relatively small in the grand scheme of things. Okay, this is a picture of the 1991 Mount Pinatubo eruption, and you can't even see the volcano here. The volcano is kind of buried under the clouds, but you can see the size of that eruption. Pretty good size. And yet, the eruption of Mount St. Helens had quite a few effects on the landscape. So we'll look at those, and we'll compare them with examples from other volcanoes. So we had the largest landslide in recorded history. And geologists don't really refer to the word landslide too much. They use the term debris avalanche for this. Just an avalanche of rock and debris coming off the volcano. And then we'll look at the lateral blast, and the blast zone can be divided up into 3 distinct zones. And then we'll look at pyroclastic flows and ash falls and lahars. Okay, and I'll explain each one if you're not sure what they are. So let's look at this hazards map here, or this devastation map, and we can see Mount St. Helens, the edifice of the volcano right here, and you can see that the pyroclastic flow, which is the most deadly thing that a volcano can do, a hot blast of ash and gas enough to incinerate everything in its path, It reached about this far. We're talking about a scale of 4 miles, maybe. We've got the scale down here. You can see the lateral blast covered this entire area, and we'll talk more about it in a minute. So this whole yellow area is the area that was directly affected by it. The debris avalanche, or the landslide, traveled almost 11 miles down the North Fork of the Toutle River here, and moving at about 150 miles an hour, just landed in the river and filled it up. And you can see here that the mud flow, they're calling them mud flow deposits, what we refer to as a lahar, a mixture of hot ash and gas and water, excuse me, ash and water. So where did you get the water? You melt, well, a couple different ways. You melt all the snow at once with an eruption, and then there's groundwater mixed in there that gets squeezed out. And so those lahars, those volcanic mud flows, reach the farthest away from the volcano. And in fact, they go off the map here. Okay, so we've got little remnants here of the debris avalanche, or the landslide, and this is found in the pumice plain just north of the volcano. And this is and this is characteristic of it, just having these kind of lumps and in the landscape, just hummocks or hills. This is part of the landslide debris. Okay, boulders are strewn around the landscape, again from the landslide, and this debris avalanche, or this landslide, advanced, I said 13 miles down the Toutle River, filled it to about 150 feet. Okay, these hummocks, these are the hummocks from Mount Shasta in Northern California. And it was always an enigma what caused these. And after watching what happened at Mount St. Helens, we were able to reinterpret these. These hummocks are about 25 miles away from Mount Shasta, which is in the background here. So obviously landslides is something that happens with a lot of volcanoes when they, you know, it happens to be a fairly common occurrence in an eruption. You get an unstable slope and then it all gives way. So that's what these have been interpreted of. These were studied very intently by Harry Glicken from the USGS after 1980. Okay, let's take a look at the lateral blast and actually that area that was decimated by the lateral blast. It can actually be broken down into 3 distinct zones. So we've got the volcano right here, the mountain itself, and then we have in this area, they're calling this the direct blast zone. And I'll show you pictures of what each of these zones look like. In this area here, in the medium orange, we call this the channelized blast zone because the trees are still standing. This was all Weyerhaeuser land. This was timberland, and it was completely changed after the eruption. So there's trees laying down. They're all facing radially away from the volcano in all directions. And then on the very outer fringes, we have what we call the seared zone. And beyond that, untouched forest. Just amazing. So in the direct blast zone, this is what it looked like. Nothing was left standing. This was forest, and it's completely gone. The trees were completely sheared off. They were pulverized and incorporated into this furious blast. So you've got hot ash and gas moving at hundreds of miles an hour. And then it's incorporating all this other stuff. It's incorporating the trees that it's just pulverized and anything that's in its path, and becomes a very, very incredible force. The channelized blast zone, here we can see the trees facing, these are mature trees. These were timber trees, mature forests, and you can see that they're all facing downwind from the blast. So you can see them all facing the same direction. In fact, when I first saw this photo, I thought, gee, it looks like grass or something. It looks like grass laying down, but those are mature trees. Let me zoom in and show you this picture. Note the size of the workers here. Okay, so that's what you were looking at. You were looking at huge trees falling down. You can see the size of the men here for scale. In fact, even log trucks are no match for it. It just, you know, pulverized everything. Okay, and this is the channelized blast zone. And then once we get to the outer fringes of this area, the trees are dead, but they're left standing. So we call this the seared zone. Now, I took this picture about 15 years later after the eruption when I visited the area and did a field camp here. And all these trees that are here now, they were planted after 1980. So you can imagine, but it was, you know, driving through miles and miles of ghost forest. What looked like ghost forest was just the outer fringe of this blast zone. Okay, and then the interface between the channelized blast zone, the seared zone, and the untouched forest. So you can see a little bit of the channelized blast zone here. In this picture, you can see out here, the trees still standing, and then beyond it, untouched forest. It's just really incredible how, you know, if you were in the right place, you just barely escaped the devastation. As was Gary Rosenquist when he took those famous shot of all those pictures. They've been now animated, you know, pictures of the blast, but this is where he was, Bare Meadow. And the, you know, the interface between the untouched forest and the scorched trees is really clear in this photo. It's right on the edge. Okay, and then I went and examined this area, and I'm calling it a tsunami in a very loose sense, but a very interesting thing that happened here and that I want to kind of share with you. So Spirit Lake was north of Mount St. Helens, and like I said, it had been America's playground. But it was also the site of what I'm very loosely calling a tsunami that was initiated by the debris avalanche during the eruption. So if you look at Spirit Lake today, you can see that there's still, and you can still see the logs in it. So this is all trees that were blown down, this white stuff in here. They're still floating around the lake. And if we zoom in a little closer on this point, I want to show you what I'm talking about here. The evidence is seen that at how high the water splashed up when the debris avalanche dumped into Spirit Lake. And I'll zoom in a little closer now. And now I think you can see this whole area here, but up to 200 feet above the level of the lake, there's no logs laying on the ground. But above that area, above 200 feet, you can see logs laying on the ground here. So this is kind of an interesting sequence of events because, and in fact, our professor kind of asked us, you know, what went on here? The landslide happened first, and the landslide dumped into the lake and caused the water to splash up, but the trees were already laying on the ground. And it washed, the water came up to about 200 feet above the current lake level, and then washed all these trees down into the lake where they're still hovering around there today. Okay, and so he said, you know, what was going on? What's the sequence of events? The landslide happened first, but by the time the landslide gets there, the trees are already down. And the landslide dumps into the lake, washes the water up, which washes all the logs from 200 feet and below into the lake. And the difference, the answer to that problem is, of course, the velocity. So the landslide was initiated first, but it's moving 150 miles an hour. So it's moving, which is pretty darn fast when you think about it, but the debris or the lateral blast is moving hundreds of miles an hour, and it overtakes it. And so it blasts down all the trees in the surrounding area. Then by the time the landslide reaches Spirit Lake, the trees are already blown down and it washes them into the lake. Okay, we'll talk a little bit about the deadliest aspect of any volcano is probably the pyroclastic flow. And this is a hot, cloud of ash and gas that happens. This is Mount Unzen in Japan, 1991, and we're taking pictures of what these pyroclastic flows look like. This is a picture recovered from Mount St. Helens. And I'm not sure of the origin of this one. Maybe some of you folks can help me out later that have more personal knowledge of this. But this person did not survive the blast, but was able to catch a picture of the blast coming towards him, the pyroclastic flow. Okay, pyroclastic flows have been probably the most deadliest aspect of any volcano. So here we have Montpellier on the island of Martinique in the Caribbean, and we have the town of Saint-Pierre here in the foreground, and here's the mountain in the background. 1902, there was an eruption of this volcano that decimated the town, totally devastated it. This was the result of a pyroclastic flow coming through. Only one person survived, and that's not him. It was actually a prisoner in a cell. It was put in there for drunken disorderly, and though he was badly burned in this underground prison, he actually survived. This is somebody looking at the devastation later. Okay, we'll look at some of the other aspects of it, and this is an explosion crater in the pumice plain just north of Mount St. Helens. So remember, all this ash was dumped. First, the landslide filled up the valley, and then all this ash from the blast filled up the valley, and this ash is still hot. And so it's mixing with groundwater here, and groundwater is contacting the hot material and then flashing to steam. And so you get these explosion craters here. This has kind of an interesting play of colors here, but that's what we believe the origin of that is. Okay, so let's take a look at the ash fall itself and see. This picture shows how far the ash traveled. Mount St. Helens here in Western Washington, and the ash traveled halfway across the United States. So if we look at ash under a microscope, most people think of ash as what you would scoop out of your fireplace, but it's not that at all. It's not the product of combusted wood. It's actually volcanic glass, little tiny shards of volcanic glass. And so when you cool rock immediately, it forms glass, maybe something like obsidian. But when there's a lot of gas involved in it, then it breaks it into, it's cooling in these little strings or little shards. And this is what volcanic ash is. And this is obviously, think of it as glass, but I think of it more like fiberglass, very easy to break up, very hard on your lungs if you breathe it, and hard on equipment and so forth as well. You know, machines, cars, and tractors, and so forth. This is a picture taken in Eastern Oregon right after the eruption, and you can see people stopping because they can just see this. They didn't even hear it in this part of Washington. If you're close enough to the volcano, the eruption was actually silent, but they're seeing this ominous cloud of ash coming towards them. So ash turns out to be a significant hazard. It blankets the landscape of Eastern Washington. So that's not snow, that's volcanic ash. And it creates a problem for homeowners, as you might imagine. This stuff is heavy. And so if you get it on your roof, it causes roof collapse. You should be wearing a mask. So much of it was dumped in Yakima, Washington, and other places. They simply did not know what to do with it. And but they simply, in a lot of places, they just scooped the ash up and dumped it outside of town, tamped it down, and built houses on it, I think. Okay, so ash is a significant hazard, but what happens when you mix the ash with water? You get an instant surge of water. You get what we call a lahar, or a volcanic mud flow. Okay, lahars mix with, they form when volcanic ash, this ash that's being blasted all over the place, mixes with melting water. So the glacier, look at, you can see the size of the mountain is already greatly reduced. And these lahars, these are the hazard that travels the farthest away from the volcano. So lahar was generated from Mount St. Helens in 1980, and several lahars, but the longest one flowed down the North Fork of the Toutle River, causing devastation, damaging houses, taking out bridges. This is the volcanic hazard that reaches the farthest from the volcano. Here I've got a picture of Muddy River on the other side, but this is how big lahars are, that they can move a rock this big. And you can see that the whole area is just kind of stained with ash. I can see trees laying on the ground. It really changes the nature of the river itself, as we'll see in a minute. I want to bring your attention to what happened in Armero in Colombia in 1985, just 5 years after that eruption of Mount St. Helens. There's a volcano that's 40 miles away. You can't see it, it's up this canyon here. Nevado del Ruiz is the volcano, and it just had a slight eruption. It didn't take much of an eruption to initiate a lahar. The lahar came down, was trapped by this canyon, the Lagunitas Canyon here. And then when it reached the plain, it spread out and buried the town of Armero. So here we had 25,000 people living in this town, and it buried up to the third floor and many feet of ash and lahar material. Now, what was so tragic about this, a couple of things. It was predicted, but the information went to Bogota, and Bogota delayed warning the town of Armero that this was coming. And so most people were taken completely by surprise by this. And in fact, they were putting their children to bed and telling them everything's okay, and then they were buried in this. And it took people several days. You couldn't get out there. You got like 150 feet of the soft material covering a large expanse, and they couldn't get out there to rescue people. A lot of people simply died in the hot sun as this ash bakes around them. It's a really gruesome thing and a tragedy that this happened. Mapping old lahar deposits gives us an idea of where these things went in the past, so we can predict where they're going to go in the future. And so this is taken from the east side of Mount St. Helens here, and you can see lahar deposits. This is kind of classic lahar deposits. You've got volcanic ash, but also the rocks that it's moving. It's embedded, it's got rocks embedded in it. So this is the kind of thing that we map these and figure out where they are so that we can make some kind of prediction for future use. Let's take a look at what the Toutle River looked like before the eruption. It was a classic northwest stream, people fishing in it, steep-sided banks, and landslide material, just normal landsliding material coming in, and a very typical northwest stream. And the nature of this completely changed after the lahar. Now look at it. It's got a very wide, flat bottom. It's got ash everywhere. The stream has changed into a braided stream, kind of, because there's so much material that the water can't really go through or move all that material. And it just completely changed the nature of the river. So every time you see a river like this, you've got to think this was the lahars. And the reason you want to know this is you want to know where they were in the past so you can predict where they're going to be in the future. Okay, what happened since 1980? Well, we'll talk about that. So since 1980, you can see that a dome has been building in the center of the crater. Now you can see this whole ramp-like structure. This is the north slope, or what's left of it. And as you remember, the mountain was way up here, the profile of the mountain. Now it's been eaten down, but you can see a dome growing in the center. And the glacier that's there is kind of horseshoe shaped. Now this dome is still active, and there's still active activity. So last time I flew over it last year, you could see steam coming out of it in places. So this is still the site of activity. And I know it looks rather small, but I was told you could fit all of downtown Portland in here. So it's actually a rather large feature. Okay, so since 1980, since the eruption, the big one, it's been rebuilding itself. And so lava domes are growing daily inside the crater. So throughout the 1980s, they've mapped this and figured out all the different growth, adding about 17 million cubic yards of lava per year as it grows. And you can see here, it actually resumed some activity in 2004. And this picture was taken in 2004. And you can see small eruptions in here, but this is just within the crater. So this isn't on a large scale. The lava dome changes shapes as new lava erupts. And so they've actually mapped it here. And you can see it's changing. They've got all the different lobes and the different times that they were added here to this thing, and this edifice keeps growing. I was really surprised, even though I knew in my head theoretically that it was active. It wasn't until I started flying over it every summer to see the hydrothermal activity and to see the effect, the effects of active volcanism really kind of made it hit home for me. So it's still very much active. So now what? Well, it's predicted that if it were to keep growing at the same rate that it has been, it will probably rebuild itself to its original size before 1980 in about 200 years. So I've got another animation here that kind of shows an eruption happening and then a lava dome forming. See if I can get it to go here. Okay, we had an eruption, and then in the inside, as long as there's magma in that magma chamber, it's going to keep growing. The dome in the center is going to, and this is what they do. This is what they all do. They basically build themselves up. The throat gets plugged, the pressure builds, it has a catastrophic eruption, and then it starts rebuilding itself. And then eventually the throat will get plugged again enough that you'll have another big eruption. Okay, so can we expect another big eruption from Mount St. Helens? Well, right now, I would say it's in the dome building stage. And so a big eruption like we saw in 1980 is in the near future is unlikely, in my opinion. But given the past history of this volcano, it's certainly going to have more large scale activity. Okay, because that's what they do. If it follows the pattern that they have always followed, then eventually we're going to have another big blast. We can't predict with certainty when that's going to happen. We can't forecast it years ahead of time and say, this is what's going to happen. So really our best defense is what we're doing now. Continuous monitoring by the USGS is the best way to do it. We're keeping tabs on all the volcanoes because, here's a picture I took from the crater, flying over the crater, and you can see the steam activity in there. There's the dome in the center. We're actually down in the crater flying around, and you can still see that it's hot in the center there. But continuous monitoring is our best defense because all of our neighboring peaks are also active volcanoes. So Mount Rainier, which I know you folks are very familiar with, and this is Mount Rainier looking from the crater of Mount St. Helens. So it's just the next one up the line here, and this is considered the most hazardous because of the lahar activity and all of the towns and all of the places that are built downstream from the lahars. In fact, we find a nice flat area. When people first settled here, they find a nice flat area and they think, well, this is a good place to build a town. It's nice and level. You have to stop and think about what made it level. Okay, previous lahars made that area level. And now, of course, our houses, our towns are built there and lots of people are downstream in harm's way. So, predicting an eruption, and it wouldn't even take an eruption of Mount Rainier. So this is, and I know other people can speak much more knowledgeably about this, so I'll leave it there. Mount Hood last erupted in 1798, and it is still, of course, very active. And it's if to us Oregonians, Mount Hood is the one in the background of Portland. Three Sisters, again, and in fact, South Sister in 2001, I think it was, or early 2000s, South Sister started swelling. And we were seeing ground deformation. So it was predicted. Look at, you can see a fresh lava flow here in the foreground. But South Sister started swelling, and that was causing concern. And then it just kind of went down. So we kind of look for ground deformation, and that's another indication. I put this in for the Portland people, for the Oregonians, but we've got the Portland metro area. Here we've got Mount Hood in the background. And we've got downtown Portland here, but you can see all these hills in the background. These are also volcanoes. These are not stratocone volcanoes. This is activity from the boring lava fields. So Portland, Oregon is one of the only large cities in the United States, maybe the only large city that's actually built in a volcanic field. Okay, there are several far-reaching effects of volcanic eruptions, and that I just want to touch on. They've been hugely important to human civilization. So we could say that the eruption of Thera, which is the modern-day islands of Santorini in the Aegean Sea, was the start of the Greek language and Greek culture. It took there were Minoans living on the island of Crete, and they had a language, they had a written language. Their island was devastated after the eruption of Thera, and the Greeks moved in, and there were enough Minoan scribes that they actually took the Greek language and put it into written language. And that was really the start of Western civilization from an eruption during the Bronze Age of Thera. Tambora, Mount Tambora changed the weather, as I mentioned. It was called the year without a summer. There was massive starvation, and that's where Frankenstein was born. The story of Frankenstein was produced over we had a whole year of dreadful, miserable, cold, cloudy weather, even all summer long. People were getting very morose, and that's where the story of Frankenstein came about. But Mount St. Helens was an important contributor to what we call modern volcanology. Back when Mont Pelée erupted in 1902, the best you could do was go clean up after a volcano. You couldn't predict it. We had several important contributions that were made after Mount St. Helens. The creation of the Cascade Volcanic Observatory and the VCAT team, that was really the brainchild of Norm Banks. It was called the Volcanic Crisis Assistance Team. It has now become the VDAP program. And these folks are still active. When invited, they mitigate volcanic hazards around the world. So Mount St. Helens brought so many new advances to volcanology that we apply around the world to keep people safe from volcanic hazards. So I want to thank you for your attention, and I'm open to questions. Should I stop sharing?